Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
Welcome to proportions and triangles. So I know that many times we look at these triangles and we don't sit there and go, okay, I can solve these little things, but we're going to look to identify some stuff. So what happens if they happen to come along and they happen to give you a segment so that it's parallel to the base, and we're just going to call this DE. Okay, so I'm going to go ahead and I'm going to sketch these two triangles below, and I'm going to make them in their minuscule because I'm just curious about what we have going on here. So we have the big triangle, A, B, C, and we have the small triangle, B still on top, right? But now it's a base of DE. So what's going on between these two triangles? What can we recognize? Well, first of all, they both share angle B. So angle B is congruent to itself because of the reflexive property. So what do the parallel lines do? Well, if you remember, when you have two parallel lines cut by a transversal, which we have, the corresponding angles are congruent. So that means angle A is congruent to angle D. Could we do the same thing for C and E? Absolutely we can, but we don't have to because now we have angle-angle similarity. So we know that these things are proportional. Okay? So the leg of this triangle, the ratio of the small to the big, will equal the ratio of the small to the big. So I'm going to call this X, and I'm going to call this whole thing Y. I'll call this W, and I'll call the whole thing over here Z. So left side is to left side, as right side is to right side. And you can think of it that way if you want. And that would be when the parallel bases are sitting down low. If you need to rotate the triangle so the parallel bases are sitting down low, go for it. Now, here's a cool fact. If this is the middle of the left side, it's also the middle of the right side. So that's kind of a cool little fact because, again, if it's the middle, that means your scale factor is 50% or 1/2, right? So that proportionality you can definitely use to your advantage. So similarity means you have a scale factor, right? And this is all due to parallel lines. Without parallel lines, this doesn't work. So here's a triangle. I'm going to make a pretty big triangle. I do like putting my base on the bottom that I'm going to be parallel to, so I can use the paper lines to also keep me parallel when I'm writing. Ooh. Now we've got lots of parts here, right? So our big triangle is going to be PQR. We'll have S to T and U to V. And now that I've labeled that, I'm going to go ahead and label my sides. So we have 12, 9, Y, 4, 3, X plus 2, and X. Okay. So we're just going to look at smallest, biggest, right, Technically we have 1, 2, 3 triangles. First base, second base, third base. So I'm going to go with this. So we got triangle QUV, that would be the small one. Triangle QST. And triangle QPR. And we know that they're all similar because of angle-angle similarity, which we just talked about, because of the parallel lines, which I forgot to actually mark. Don't forget to mark those if you're given to you. That's kind of the whole reason why we can do this. So we're just going to talk left side. I'm not going to say small, big, because I don't know whether the left side, right side, bottom. And I'm going to leave it blank if we don't know anything about it. Okay? I did forget to write one number down. I'm supposed to write 30 right here, and actually I forgot to write a couple of things down. Okay, so the left side of QUV is 12, the right side is 9, and the bottom is Y. QST is 16, 12, and Z. And then QPR is X plus 18. The right side is 12 plus X, and the bottom is 30. Now, we can make proportions using these, but I want to use these two triangles right here. Okay? And I want to look at the left side and the right side. So left side to left side equals right side to right side. It's a nice thing about making this little chart is it really helps us out. Okay? So even though I messed up right, I almost wrote just an 8 instead of an 18. So what are we going to do first? We're going to pop in those cross products, right? 12 times x plus 18 equals 16 times 12 plus x. Okay. Now we could just distribute and solve. I am going to show you a quick fun little trick. 12 and 16 are both divisible by 4, so that means I can divide both sides by 4. We can actually make this 3x plus 18 and 4 times 12 plus x. If you ever want smaller numbers, that's a neat trick you can do. So we'd have 3x plus 54 equals 48 plus 4x. I'm going to move my x's to the right and my numbers to the left. And so when I do that, I will have 6 equals x. So could I have just distributed the 12 and the 16? Absolutely. I decided to go ahead and just make my life a little bit smaller numbers. And my dog decided to come visit, so sorry about that. Okay, so with that in mind, we can come back up here. 6 plus 18, this is now 24, and this is now 18. Okay, so I actually know everything about all the left sides. Perfect. What I don't know is everything about the bottom. So I can compare my smallest triangle to my biggest triangle. And so 9 is to 18 as y is to 30. So some of you might already know that since this reduces to 1/2, this has to be reducible to 1/2, so that makes y 15. Others might need to see 270 equals 18y, then divide 15 equals y. Okay. Now the next one we might do is, could we still use the middle one and the big one to get z? Absolutely. So we've got 12 is to 18 as z is to 30. Cross product. (18z) equals 360. So z equals 20. And now we've solved for each of them just because of proportion. Again, I like making this chart because I can easily see my proportion. I can use, this is these two, these two, these two, these two, these two, these two. I can make a fraction proportionate out of any two. And that's kind of the reason behind that chart. You can also notice that, let's go ahead and write these numbers in here so we can see it. Y was 15, Z was 20. Okay, so if I take the bottom row and I multiply it by a scale factor of 4/3, I get the 16, 12, and 20. So I could have even compared the two small triangles. Also, let's come back up in the picture, and I'm going to label everything in the picture so we can see a few more things. So X turned out to be 6. So this turned out to be 8. Y turned out to be 15. Z was 20. So do you see how we can take these two numbers and multiply them by 2 and get these two numbers? Or we can get these two numbers and we can times them by 3 and we can get those two numbers. So not only are there proportions between the three triangles, the way that it evenly split up the sides, there's proportions there as well. So you can actually use that. You can use this is to this. You can use this is to that. All these proportions in there are kind of really cool so that we can use it to see relationships with side lengths. So triangles with parallel lines coming across them create proportionality. So I'm going to kind of back that up and we're just going to look at another triangle and make sure that makes sense. Oh, hey, come on, a little blurry. Okay, so here we have 16, we have x plus 2, we have 12, we have x. So instead of doing 16 to the whole thing, instead of doing 16 is to x plus 18 and 12 x plus 12. Instead of doing that much work, which is what we did before, I'm just going to do this. So now we have 16x equals 12x plus 24. Subtract that over, 4x equals 24, x equals 6. Happens to be the exact same thing that we got, but maybe the numbers were smaller so that you didn't need my little trick. So that's what happens whenever we have parallel lines coming through. Okay. However, that's not the only way we get proportionality because of our angle-angle relationships, right? Okay, let's say you have triangle ABC and you decide to bisect angle B. We'll call this point right here D. So BD is your bisector, okay? Which means those angles are the same size. You can prove that this creates ratios because of angle-angle similarity. So I'm going to go ahead and let's see if we label this. We'll label this Z, this W, this X, and this Y, just for simplicity's sake. So we are going to have ratios and it's basically going to be a scale factor between the two. For example, A to D, which is where we have our X, is going to be compared to C to D, which is where we have our Y. That's going to be like our A to B, which is where we have our Z, which will be like our W to B, which is where we have our, it's not W to B, C to B, depends on which part you're looking at, right? Which is where we have our W. So let's mark those here. I'm going to put a pink line on A to D. Okay. And I'll put a green line on C to D. So they got split up because the angle got cut in half. Okay. However, our A to B was how far we were away from that vertex that got cut in half, and that was our Z. And our C to B okay. So how far are we away from B, from the vertex? How far are we away from the angle bisector? How far are we from the vertex? How far are we away from the angle bisector? That's what it's creating. And it's still creating this proportionality. And it can be proven with angle-angle similarity. So how is that going to help us? Okay. Well, I've got to, it's going to help you because you're going to know that angle relationships angle relationships exist. And if you want to see the proof of that, we can get the proof of that. But I know a lot of people are like, okay, come on. I just want to be able to do my math homework and get it done. Alrighty here. Here's our triangle. This whole side is 13, this is 10, this is 16. And this angle bisector comes in, cuts the angle in half, and labels this X. And you have to find X. Well, unfortunately, you need both parts. So if this whole thing is 13, and this side is X, how would you get the other? For example, if this was 4, what would this be? How'd you get that? You subtract it. So this side would therefore be 13 minus X. Okay, so distance from the vertex, distance from the angle bisector, distance from the vertex, distance from the angle bisector, and lo and behold, boom, a proportion. Yay, proportions, we can cross product, right? I know you guys are so excited about cross product. That's going to be the best thing you guys take away from geometry class and you take back to your algebra class. Okay, so we're going to have to add the 10x to the other side. And x equals 5. So one side is 5 and one side is 8, and that's, hey, that makes sense. Because 5 doubled is 10, 8 doubled is 16. There's some ratios going on in there. That's not a bad deal. We like that. So usually if you're cutting triangles up somehow, it's resulting in a specific relationship, and you just need to remember that. So look for the proportions, look for the angle-angle similarity. If you can't find it, redraw your triangles separately and make sure you're comparing apples to apples.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Then drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.